Okay, so today we're going to be talking about section 2, which is trigonometry. And I think the big thing is remembering from geometry, you talked about there are trigonometric ratios that will you can write based on at a certain angle, you could answer the question. And that's still true. There's right triangle trigonometry. There are other things we're going to talk about, but the first thing is that trigonometry is a specific ratio from a specific perspective. And then also we're going to use theta to represent certain angles, and that's how you spell it. And normally when you were younger, you kept theta between 0 and 90 degrees. Okay, it wasn't ever 0 and it was never 90. And you talked about acute angles. And so that's what we're going to begin with now. We will expand this over the next couple days, but for right this second, that's what we're going to speak about. And I think the big thing is if you stand at a specific angle, okay? So say that you stand at the angle B, okay? And you put theta there. So from theta's perspective, you know the hypotenuse is always the side that's across from the 90 degrees. And that doesn't change no matter where you stand. If you have a right triangle, the hypotenuse is always the longest side. It's the one that's across from the 90. And what does change would be if you've got a right triangle, the leg that's closest to the angle is called the adjacent leg. And the leg that is across from that angle is going to be called the opposite leg. So if you're standing at this theta right here, the hypotenuse will be AB. The adjacent leg, the one that's closest to that angle, and notice it touches the angle, is going to be CB. And then the opposite leg is going to be the one that's AC. It's kind of like if you are speaking fancy, your adjacent neighbor is the one that's next to you. The opposite one would be the one that's across the street. And so it's a fancy way of speaking of it. Now, if you change your mind and you're like, okay, I'm going to go stand over at A, well, the hypotenuse stays the same, but the words for adjacent leg and the opposite leg would be interchanged because the adjacent leg to A would be AC and the opposite leg from A would be BC. So we're going to stick with just standing at theta, standing at angle B to answer these questions. But you probably have learned SOHCAHTOA. You probably remember that from last year. So the sine is the opposite leg over the hypotenuse. The cosine is the adjacent leg over the hypotenuse. And the TOA is the opposite leg over the adjacent leg. And those are 3 of the possible ratios you can learn. We're going to learn 3 more today. The reciprocal of sine, okay, meaning its flip, okay, is going to be cosecant. Okay, if you do the hypotenuse over the opposite leg, you're going to do cosecant, and the abbreviation is CSC. Cosine's reciprocal would be the hypotenuse over the adjacent leg. And tangent and cotangent are just reciprocals. Cotangent would be the reciprocal, which would be the adjacent leg over the opposite. So we've got 3 new ratios we're learning this year, okay? And they are shown by cosecant, secant, and cotangent. Okay, and so not a humongous deal, but those are the 3 things that are new. And so I think if you look at this and be like, okay, well, if I would stand at theta, okay, theta would be angle A. And you said, okay, what would be sine? Sine would be the opposite leg over the hypotenuse, and you reduce it and rationalize it. The cosine would be the adjacent leg over the hypotenuse, so it would be 15 over 17. And then tangent would be the opposite of adjacent. So that's what you learned last year. Now you've got to remember, you can speak about the reciprocal, not their inverse, but the reciprocal of each of these. Sine would go with cosecant. It'd be nice if sine goes with cosine and cosine goes with cosecant, but it doesn't. Sine's reciprocal is cosecant and cosine's reciprocal is secant. Tangent and cotangent would be reciprocal. So you would answer those questions. And so I think the big thing is, stand at G and let's name the sides. Okay, so the hypotenuse is right here. and then there's two legs. The legs meet at the right angle. The side that is the leg that's closest to the angle is going to be the adjacent leg. That means fancy means it's close. And then the leg that's opposite from that would be the opposite leg. So let's answer these questions. So I'm going to set it up and be like, okay, and here's what I would say for you guys. I would say, let's do sine. Let me get a pen instead of a highlighter. Sine of theta is equal to, and then there's cosine, and then there's tangent. And then the reciprocal of sine would be cosecant of theta. The reciprocal of cosine is secant. And then tangent is cotangent. And so let's find the first three fractions, and then we can flip them over to find their reciprocal. So sine would be the opposite leg over the hypotenuse at 24/40. And we can and should reduce it, divide each one by, it looks like 8. And so we're going to get 3/5. And then cosine would be the adjacent leg to angle G over the hypotenuse, and we can and should reduce it to be 4/5. And tangent should be opposite over adjacent, so it'd be 24/32. And the reduction of that would be 3/4. How do you get these other ones? We'll just flip them over. Make sure you rationalize as needed. And I think as long as you kind of set this up to be like sine, cosine, tangent, cosecant, secant, cotangent, you should be set. So we're learning just the reciprocal, not the inverse, but the reciprocal functions of each of these items. Okay, so let's turn the page and let's look at the next one. The next one really is the same exact triangle, but they're saying, can you, instead of standing at G, stand at F? And so from F's perspective, this is still the hypotenuse. This is now the adjacent leg, and this is going to be the opposite leg. Okay, so let's write down what we're doing. We're going to do, from angle F's perspective, we're going to do sine of F, cosine of F, tangent of F. The reciprocal of sine is cosecant, and we've got secant, and we got cotangent. Okay, so sine from F's perspective is the opposite leg over the hypotenuse, which would be 32/40. And when we reduce it, we do get 4/5. And then cosine is going to be the adjacent leg over the hypotenuse, which would be 24/40, which will be 3/5. And then tangent from F's perspective is the opposite leg over the adjacent leg, and that reduces to be 4/3. Notice, let's see, now cosecant would be 5/4. This would be 5/3, and this would be 3/4. Okay. And I think the thing that I want you to notice would be, if I ask you to say, what would be sine and cosine of the two acute angles? If you did the Pythagorean theorem, you would get 5 squared plus 12 squared equals x squared. That's 25 plus 144 is 169. Square rooted is going to be 13. So 5, 12, 13 actually is a Pythagorean triple, because all three sides are nice. But if you go to find sine from D's perspective and cosine from D's perspective, because sine is the opposite leg over the hypotenuse, and cosine would be the adjacent leg from D's perspective or the hypotenuse. When you go to find the sine from F's perspective and then the cosine from F's perspective, you're going to notice that the sine is going to equal, from F's perspective, 12/13. And then the cosine is 5/13, because from each of those acute angles perspective, the opposite and the adjacent are interchanged. So sine from D's perspective is going to be the same as cosine from F's, and then vice versa. Okay. And it has to do with, if I find the cosine from 20 degrees perspective, that equals the sine, okay, of whose? Its complement. Okay. What do you mean complement? Well, the complement is what makes 90 degrees. So if you stand at 20 degrees perspective, okay, in a right triangle, like, ooh, I want to do cosine, you would end up doing the adjacent leg over, let's say, the hypotenuse, okay? But if you go across the triangle to its complement, to its 70, finding sine would give you the exact same. It would take the opposite leg over the hypotenuse, and that would be the same fraction. So complements, the sine of a value is equal to the cosine of its complement, and vice versa. So I want you guys to realize complements, sines and cosines will be congruent in their answers. And then another thing I would say is this. If I say what is the product of the tangent from A's perspective times the tangent of B's perspective? Well, what do you mean? Okay. If you go to A and you say, okay, I'm going to do the opposite leg, okay, over the adjacent leg. Okay, that's A over B. And I'm going to go over to B's perspective over here, okay, and I'm going to do the opposite leg over the adjacent. I'm going to get the reciprocal. And whenever you multiply reciprocals together, what do you always get? Well, you get 1. Okay, so if you do the tangent of an angle times the tangent of its complement, okay, complement means they plus to make 90 degrees, then you're always going to get 1, which is kind of cute, okay? Now, the next thing to talk about would be, can a sine ratio ever be greater than 1 or a cosine ratio? Well, the answer is no. Why? Because sine and cosine are going to be leg over the hypotenuse. And whenever you put a leg over the hypotenuse, you get a fraction that's smaller than 1. Okay, and so therefore, no. The leg over the hypotenuse will never be an improper fraction, never going to be bigger than 1. Well, this other question would be, could tangent ever be bigger than 1? The answer is sometimes, yes. Because it's the ratio of the legs, and it might be proper, it might be an improper fraction. Same with cosecant and secant. Yeah, those can be bigger than 1 as well, okay? And so, absolutely. In fact, they most of the time are. We're going to exclude the negatives, but we'll talk about that later. Okay, and then I think the last two things we're going to discuss today would be, we're broadening towards making, finding tangent ratios, sine, cosine, tangent, etc., of angles that are larger than 90 degrees. Okay, and so how would we even do that? And there's like a formulaic way to do it. But there's also a graphical way to do it as well. And so I think I want to talk to you guys about how would you do this, okay? I think the first thing is it says the terminal side. Now, terminal side means you're graphing an angle that is going to be on the unit circle, okay? And so remember, the initial side is going to be right here, pointing to the right, and the terminal side is going to be formed when you plot this point, okay? This point is going to be the point 3, 4. Not 4, okay? 1, 2, 3, 4. So you'd plot that point. And so step 1 is draw your initial ray. The second one is going to be plot the point, connect it to the origin, okay? That's the angle that we're making, okay? The following step is to drop an altitude to the x-axis. So many kids think, hey, maybe I can go to the y-axis. The answer is no. Okay, no matter what quadrant that point falls in, it always goes to the x-axis. So even if it's right here, it's going to be dropping to the x-axis. Or if your point is going to be in the 3rd quadrant or the 4th quadrant, connect it to the origin and draw an altitude towards the x-axis. Never the y, always the x. Okay, so and then you're going to put the theta, okay, the angle between that ray and the x-axis. Okay, so that's going to be your theta. Your theta here would be right here. Your theta is always in between the ray and the x-axis. And I can draw another picture. I say that it's in the 3rd quadrant. You drop it to the x-axis, and your theta is always formed between that ray and the x-axis. Now, the truth is this, okay? When you draw these rays, you know full well that they begin at 0 and they flow through here. But the reference angle is the angle we're going to focus on. Okay, the reference angle is the angle it makes with the x-axis. So although this one in the second quadrant has your theta here, we're going to call it theta prime is going to be the reference angle, the one that we're going to deal with and say, yeah, she may want us to find sine, cosine, and tangent 120 degrees, but how we bring this down to size is we focus on the reference angle or theta prime, the one that keeps it in our ballpark, keeps that angle smaller than 90 degrees, is the angle that's formed between that ray and the x-axis, okay? And so this one in the fourth quadrant, yeah, I know your original theta is all the way over here, but the theta prime, the theta we're going to focus on, okay, to make it, high school age and appropriate, is going to be formed between that ray and the x-axis. And that's where we do our actual trigonometry. And how you actually do it is you're going to form a right triangle, using that theta prime. Okay, so copy down these ones here. And I would say you're looking at the x coordinate is 3, the y coordinate is 4. Okay, your legs could be positive or negative, directionally speaking, as to depending which way you go to get that point. So this point over in the second quadrant could be -3 and up 4. Okay, the one in the fourth quadrant could be -3 and down 4. Your legs of your triangle can and will be negative at some points. Pretend this next one would be 3 and then -4. Okay, directionally speaking, your legs can and should be negative at some points. However, your hypotenuse will never be negative. Okay, what do you mean, woman? Well, when you do the Pythagorean theorem to find the hypotenuse, you put the x coordinate in parentheses and your y coordinate in parentheses, and that will give you your radius squared. Okay, the radius will always be positive because no matter whether your x or y is negative, it goes in parentheses. So when you end up squaring it, they become positive. Okay, so your hypotenuse will always be a positive value. So 9 plus 16, I don't know why I put a 4 there. 9 plus 16 is 25. Square root of that is going to be r is 5. Okay, so this is going to be a 5 for the hypotenuse. So from theta's perspective, you're going to answer the question as to what is sine, cosine, tangent, cosecant, secant, and then cotangent. And what you're focusing on is that theta or that theta prime, okay? So if it's more than 90 degrees, you're going to focus on the theta prime, the angle, that red angle that I drew in each of those quadrants, that's going to be smaller than 90 degrees. So even though if I'm like, oh, find me the sine, cosine, tangent of 300 degrees, you're really going to focus on the angle it makes with the x-axis, okay? And so sine from this angle right here is going to be 4/5. Cosine would be 3/5. Tangent would be 4/3. Cosecant would be hypotenuse over the opposite, and then 5/3, and then 3/4. Okay, so those are going to be those answers. Always reduce and rationalize your answers. Okay, now let's move this to another quadrant. Okay, and I think that's really where kids struggle. Okay, so let's start by making the axis. And so here's the x-axis here. There's the initial ray. And then the point is going to be -7, 4. So -7 and then up 4. So you plot that point. Okay, notice it's in the second quadrant. You connect it with the x-axis or with the center. And yeah, this right here is theta. But that's obtuse. Nobody wants to find sine, cosine, and tangent of an obtuse angle. So even though that is theta, we're going to call this theta prime. The reference angle, the angle it forms with the x-axis. So drop an altitude to the x-axis. Again, remember, even if you're in the third quadrant, that theta prime is between that ray and the x-axis. Even if you're in the fourth quadrant, it's between that ray and the x-axis. So theta prime is who we're going to focus on. You may want us to find something weird, but I am going to find this. Okay, something's going on outside. Okay, so let's label these rays. Okay, so this is left 7 and this is up 4. Let's find the hypotenuse. So you go -7 squared plus 4 squared equals c squared or x squared, whatever you want to call it. And then that means you got the square root of 65 for c. Okay, so that is going to be, again, it's always positive. If you can break it down, great, do it. Okay, and now what we're going to do is answer the questions. Okay, so let's do sine of theta. We can call it theta. It's equal to doing theta prime. Okay, but we have to focus on this theta prime right here. That's where we're going to look at it. So sine of theta, cosine of theta, tangent of theta. We're kind of cheating, but we're really doing a good thing. Okay, this is cosecant of theta, secant of theta, and cotangent of theta. Okay, here we go. So sine from theta's perspective is going to be 4 over the square root of 65. Oh, that's cute. Okay. Yes, you should reduce and rationalize. So times top and bottom by the square root of 65. So you get 4 square root of 65 over 65. Now, while we're here, let's think about this a second. I've got to flip this over to get cosecant. You can choose to flip over the reduced answer, the rationalized answer, or the original. I'm going to flip over the original. Why? Because then I won't have to re-rationalize anything. If I put down the square root of 65 over 4, okay, which I flipped over this first one, I'm done. Okay, so let's look at the second one. If I take cosine, I'm going to get -7. Yes, you can get an answer over the square root of 65 with a negative on it. And rationalize, you get -7 square root of 65 over 65 because I times top and bottom by the square root of 65. So that's this, and I've got to flip over the original or the reduced form. I'm going to flip over the original, and I'm going to get the square root of 65 over -7. Okay, and you can put the negative in top or bottom or, either one. Tangent would be 4 over -7, and the cotangent would be -7 over 4. So those would be your values. And I think what I would ask you to do would be, in, preparation, okay, what if I told you do 5 over 0? What would that number be? Well, that would be undefined, okay? And sometimes we're going to find sine, cosine, or tangent of undefined values. What if I did 0 over 5? What would that give us? Well, that would give us 0, okay? And so I want you to think about, sometimes using those values, as we're working. And also one thing I want to talk about real briefly would be, we are going to be using this chart here. It doesn't make the most sense for us to do a ton with it right this second, but there's a way to actually look at some ordered pairs and to glean these answers moving forward. So we're going to be building a unit circle in about 2 days where we can say, if I know the point, okay, this point right here, can I find the values of sine, cosine, and tangent? And so we will be discussing this further moving ahead.